the title is supposed to just remind us that given the spectacular developments and experiment, the discovery of the Higgs and how incredibly well the LHC has been working, that this is the time in our subject that we should be thinking about the 20-year future of the field, which is what SUSY 2033 was supposed to refer to. To my mind, the 20-year future of the field is a 100 TeV proton-proton collider, with the circular E plus E minus option as being a very, very important complementary feature to it. So that's what I want to talk about, motivations for going to 100 TeV. And first and foremost, before anything else, before talking about physics cases and what we might learn and so on, the most obvious reason to go to 100 TeV, that's the obvious future of our field. And, you know, we've gotten used in fundamental physics to attracting the very, very best minds on the planet, promising them essentially nothing other than pain and suffering for 30, 40 years to work on the most difficult problems humanity has ever faced in science on very long-term timescale. How do we manage to do that? It's because the word big is sitting there in every aspect of what we do. Okay? It's big physics, big ambitions, and big machines have been and will be the lifeblood of our field. So that's the most obvious reason to do it. It's the frontier. We need to go there. We can go there. We should go there. And of course, also obviously, how to proceed will depend on the first LHC-13 results. But in fact, in every scenario I can now imagine, we will need the 100 TeV proton-proton collider. And I want to emphasize, this isn't just sort of, it's not just hype. Had the LHC discovered 250, 300 GeV gluinos, you know, light superpartners and so on, it's not obvious that we'd necessarily want to go to a 100 TeV collider. In that scenario, you might want to study things at a lower energy plus E minus collider. You might want to do. It's precisely what's been happening so far. The fact that we discovered the light Higgs, but no new physics, that now makes it more motivated, ironically, to go to 100 TeV than had we discovered lots and lots of light new physics. And so that's what I want to spend some time talking about. This list is by no means exhaustive, and it's also not, there's a number of studies underway of the ability to address some of these questions. So this is more a sort of a program of research and thinking, and I'm sure many of you can come up with other sets of motivations that is all worth exploring and studying. Just the physics, just the collider physics of a 100 TeV machine has so many fascinating novelties in it. You know, top quarks are bottom quarks. Electroweak Sudakov logs are now important, so we have W and Z jets. There's so much, there's so many new things to think about. But what I want to talk about is the physics motivations, what we might learn from it. And so the first thing, to my own personal mind, the most important thing is that the 100 TeV machine is what we need to really settle the ultimate fate of the question of naturalness. And we've all talked about this issue at such great length that I don't want to spend too much time on the philosophy, but I want to say a little bit about it. First, the discovery of the light Higgs is absolutely critical. Okay? So it is unfortunate that the way we've talked about this to graduate students, to the general public, never mind to ourselves, is that, well, the Higgs was the sort of boring thing, the simplest thing, and that's what ended up being discovered. In fact, it's shocking that anything like a light elementary Higgs describes the physics of electroweak symmetry breaking. Nowhere else in nature have things ever looked like that before in a state of nature. And so if we think of new physics as something new that we haven't seen before, the Higgs is already quite new physics. Okay? We've never seen anything like this physics anywhere else in a state of nature. And nature hands us tons of effective field theories that we can study in the lab in condensed matter systems. Okay? In none of those effective field theories do we ever encounter a light scalar field without fine-tuning. That's a triumph of the idea of naturalness. That's even where it came from. The indication that that's not what our universe looks like right now, the fact that we see in our vacuum a light Higgs, means that our vacuum is qualitatively different than a randomly crappy condensed matter system. Okay? It's not a crappy metal. It's something really novel and new. And indeed, just repeating, the only time we've seen this before is when there's been someone out the outside twiddling the dials to bring the system, by fine-tuning parameters, close to a phase transition, either thermal or quantum phase transition. Now, as I'm sure you've all heard, this idea of naturalness was not invented out of thin air by Wilson and 't Hooft. In its modern technical form, in quantum field theory, it was talked about in that language, but this general principle of naturalness, the general principle has been invoked before, and the issues have occurred before. In fact, 3 times in the last 100 years, naturalness issues occurred, and every one of those times, they were resolved in the way many of us expected it to be resolved in the case of the hierarchy problem. So very quickly, reminding you of some of these things, I'm sure you've all seen these examples. 100 years ago, there was the problem of the classical self-energy of the electron that was infinite, and if you cut it off at some length scale, to get an estimate for the length scale where the energy is comparable to the mc squared of the electron, we get this length scale, which is the classical radius of the electron. And so people tried to make models for the electron where it had a finite size at that scale. That was the technicolor of the early 1900s. And those models were wrong. They had theoretical difficulties, much like the technicolor of the 1980s. Okay? But the basic principle was correct. There was new physics. The new physics was dramatically different than what people expected. It was electrons and positrons, quantum mechanics and relativity, but their logic was correct. The new physics did come in by the scale where they thought it would. In fact, it came in earlier than it had to. It came in 137 times larger distance scales than it needed to. So naturalness worked in this case so fantastically, no one was talking about whether there was 10% cancellation between different contributions to the mass of the electron. That's because there's a weak coupling. And when the theory is a weak coupling, the corrections should be small compared to the leading piece. And indeed, that's exactly what happened. But anyway, this is a spectacular success of naturalness. Another example you all know is, here's literally the analog of the hierarchy problem. We draw the hierarchy problem diagram for the charged pion. We get a quadratically divergent contribution. At this point, you could say, oh, what do I know about quadratic divergences? It's all meaningless, dim reg, conformal, blah, blah, blah. I don't care about this. Or you could do what always works in physics, take the pragmatic attitude, you do the estimate, and you proceed. And here you say there should be new physics beneath some scale lambda. The scale's got to be beneath 1.2 GeV. That's a correct prediction. The new physics was the rho meson. It also came in earlier than it needed to at 770 MeV, which is again a weak coupling factor. In this case, a weak coupling is 1 over square root of n. Okay? So when this is it's occurred before and it's always worked, and in fact worked parametrically and worked better than it needed to. The third example is KK bar mixing. Okay? So, and in fact, these two ideas have analogs in how we solve the hierarchy problem today. The analog of the first method is supersymmetry. The analog of the second method is the Higgs is a pseudo-Goldstone boson. Okay? But the problem, of course, as we all know, is where the heck is everybody? Okay? So if we apply exactly the same logic, the question is, where is everybody? And as, of course, you also know, this is not something new that's being shoved down our throats by the LHC. This is not like everyone was expecting zillions of new particles, and then now, for the first time, because of the LHC, we're concerned about the idea of naturalness. There's been a tension from day one in thinking about physics beyond the standard model, which is the famous fact that if we believe it's a standard model and nothing else up to high energies, we have a beautiful standard model explanation for approximate symmetries, which is broken if there are new physics at the TeV scale. That's been a tension from the first day of thinking about this. And in fact, that's for a large reason why the field of beyond the standard model existed as an interesting realm of intellectual activity. Because you had to think of new physics that could solve the naturalness problem while not giving you all of these big effects. So they are thought of as not problems, but opportunities. That may well still be the case. But there's an early indication of something that did not quite look like the previous times when this kind of logic held sway. No new physics so far at the LHC is putting the broad idea of naturalness under, to my mind, somewhat more pressure. Although, if you had to ask me, am I right now more worried about whether low-energy supersymmetry will be discovered at the LHC or not, I would say I'm not particularly more worried than I was before the LHC. That's because I was already somewhat worried before the LHC. Okay? And of course, I'm not alone. Okay? Not, of course, the situation will change dramatically at at 13 and 14 TeV. That will take it into really new territory beyond what we were forced to thinking about before. Okay, so naturalness has worked dramatically before. The little indications now that the situation might be a little different. Is it a big deal or not a big deal? It's not obvious. But it's also worth remembering that naturalness has failed dramatically before. You have to reach very far back to come up with the first dramatic example. The ancient Greeks, Aristarchus, had the heliocentric model of the solar system. He understood everything. And his colleagues rejected it because it was very unnatural. It made a prediction, the parallax of the distant stars, which is just too small to be seen by the naked eye. And you could explain it if you said the distant stars were so much further away even than the sun. And they said, that's ridiculous. The sun is already so far away. Now you're going to say that that one thing is really close to us and everything else is ridiculously far away? Lucky for you and your model, right? That they didn't understand the dynamics. Gravity, things attract each other. You know, they thought things were moving along tracks on a big celestial sphere. So instead of having that crazy hierarchy of scales, they rejected this model. In fact, Tycho Brahe had a model around the same time, a little earlier than Copernicus, where he had everything going around the sun, but the sun going around the Earth to not have the parallax problem. Okay? So anyway, so this is one early example where people's mistaken notion of naturalness led them to reject the right answer. This is so early, though, that maybe it's not relevant for today. If we go much closer to home, if we go one energy scale down from particle physics to nuclear physics is a confusing subject because it has little accidents in it. Okay? The deuteron binding energy is somewhat small compared to nuclear physics scales. That's not maybe that dramatic, maybe a 20, 30% accident. A more dramatic fact is that two neutrons are not bound. And the amount by which they're not bound is 60 keV. Okay? They come so close to being bound, they miss by 60 keV. 60 keV is much smaller than all the other scales in nuclear physics, and this just looks like a percentage level accident. So we go just down, in particle physics, we go down one scale to the nuclear scale, and there are two tunings. In fact, there's an effective theory by Kaplan, Savage, and Wise that describes these few nucleon interactions. It has two 4 Fermi couplings, giving the isosinglet and the isotriplet interactions between the nucleons. And both of those couplings are fine-tuned to be somewhat close to an ultraviolet fixed point. Okay? Unstable ultraviolet fixed point. There's an accident. There are accidents in there. They're not huge. They're percentage level accidents. But that just shows we go down one energy scale, and these percentage level accidents are actually sitting there. It's amusing that these accidents are plausibly related to up and down quark masses, and therefore are at least related to the physics of electroweak symmetry breaking. Okay, so in nuclear physics, a part of it that perhaps depends on electroweak symmetry breaking seems to have these little accidents in it. Now, today we have a modern version also of a humongous problem, which is the cosmological constant. This is sort of the crushing weight on the notion of naturalness. As we all know, we apply exactly the same logic to the cosmological constant problem as the hierarchy problem. We make a manifestly incorrect prediction of new physics at the millimeter scale. And so we've all known this for a long time. And you could say, oh, that means naturalness is crap. That also means that someone could have said in 1960, why should I care about the quadratic divergence for the charged pion when there's a cosmological constant problem? And they would have been an idiot to do it back then. Okay? The problem is, in physics, we don't know. You can use a historical analogy to illustrate any polemical point you want to make. We don't know what's going to happen, right? But this is telling us that there are things on both sides of the naturalness argument. Sometimes it's worked, sometimes it hasn't worked. When it's worked spectacularly. Sometimes it's not worked spectacularly. Sometimes it's at this percentage weird intermediate level. What's going on today? I don't know. That's, I think, to my mind, the most interesting question on the table today. Of course, when it comes to the cosmological constant, the only idea we have, the only scientific idea we have for why the cosmological constant might be small invokes a humongous multiverse. And having us sitting in a tiny region of that otherwise huge and lethal space where the universe isn't empty or otherwise completely inhospitable. And it could be that if we start accumulating more and more evidence for fine-tuning in the parameters of the laws of nature, that we'll get more circumstantial, I stress very circumstantial, evidence, but more of a push towards this quite radical picture of the world. And even circumstantial evidence would be something very, very valuable in order to start taking this kind of picture more seriously, at least studying it more seriously. So, this is all just to say that, at least to my mind, this question of is the weak scale natural is the central question of our field right now. The stakes are huge, and it's not just this or that particle, okay? Discovering this or that particle. There's a deep and structural issue at stake at the foundational heart of fundamental physics that we have to get some verdict on one way or the other. So we're at this, again, very important fork in the road. Are things going to be natural or unnatural? For a long time, we thought it was going to be natural. If so, there will be big new principles. Fantastic. If it's unnatural, that's an even bigger paradigm shift compared to what we were anticipating. Does it look more like the cosmological constant? Okay? And then the crucial question is how tuned? How tuned is it? By the way, when I say how tuned, I really mean maybe you can say we're thinking about it all wrong. We don't. That's fine. Okay? But we can compare it to other instances where we've seen this kind of physics where we have to do tuning, and we can ask, if it looked like that, how much tuning would it be? Okay? So that's an invariant question that we can ask and get the answer to. Now, suppose we see the Higgs and nothing else at the LHC. That would tell us there's a tuning of about 1% in electroweak symmetry breaking. And now you can ask, is that convincing? Well, I won't be convinced that that means that there's fundamentally tuning in the underlying laws of nature. And one reason is that, as we just discussed, there are many percent-level accidents that we've seen. We talked about one of them, just in nuclear physics, one scale down, the unbinding of two neutrons is a percentage level accident. That fact is known to anyone who's studied the fact that there's no two neutron bound state. It didn't lead people before supersymmetry to go around saying there's no naturalness, it's all crap. You say percentage, you shrug your shoulders. Things happen, maybe it's okay. There's the famous fact that the quadrupole of the CMB was low. That caused the problem. That was a case where the physics came in at the 11th hour. Later than the theorists were predicting. And now we understand why. It just looks like an accident. It's a percentage level accident. There are sillier things. The moon eclipses the sun almost perfectly. That's a percentage level accident. Okay? I have no idea what anthropic justification it has. In fact, it has a misanthropic justification of killing many Mayan virgins. But it's just an accident. So let's say we discover that there's tuning at the percent level at the LHC. That would add electroweak symmetry breaking to this list. But I think a lot of people would still go around shrugging their shoulders. I mean, it would be fascinating to add it to this list, but it would not be a knockout blow. So how will we know? The most obvious thing to do is to go to higher energies, obviously. Okay? I'm sorry, this talk is filled with totally obvious statements, but you have to listen to me. So, all right, so obviously we go to higher energies. We might find something. End of discussion, right? And then the fact that maybe it was percentage tuned or not, no one will care. It'll be like the two neutrons problem. Maybe in 30 years, people will come back and scratch their heads and wonder what it means. But we'll be so busy in the meantime figuring it all out that no one will care about this question. Okay? Now, we might find nothing. If we continue to find nothing, that gives us a quadratic gain in the degree of tuning from the center of mass energy of the machine. Okay? Of course, we can also look for rare processes and precision measurements, which are important, but they're indirect. And because almost all of these are dimension 6 operators, even constraining them gives us only a linear gain in tuning indirectly, versus directly, where you get a quadratic gain in tuning and it's direct. Okay? So because of that power of 2, if we see the Higgs and nothing else at a 100 TeV collider, then we're down to 10 to the minus 4 level tuning. Now, if you want to continue to shrug your shoulders, you can do anything you want. You know, it's a free world. But there is an invariant fact. The invariant fact is that this degree of tuning will be 100 times worse than any other tuning we've seen anywhere else in physics, other than the cosmological constant. Okay? So we have never seen this level of tuning in particle physics, and it's dramatically new. So right now, the situation is that we thought the Higgs could be perfectly natural. Now maybe it's percentage tuned and it's this muck with all this other accidental things. And the question is, does it emerge from that muck and cleanly separate itself from those earlier examples, heading towards looking more and more like the cosmological constant? Okay? I think this factor of 100 is a big, big deal. And even seeing the Higgs and nothing else at 100 TeV collider would, again, in a sense, be the most shocking thing we could discover. But this time it will be harder, at an invariant level 100 times harder, to shrug our shoulders about it than it may have been before. So even this so-called worst-case scenario would be 100 times more shocking and dramatic than no Higgs at the LHC. And to my mind, and I think to most of our minds, would put a nail in the coffin of the idea of naturalness. This alone fully justifies the march to 100 TeV. I should say that the circular ± machine Higgs factory plays a very important and complementary role, again, by giving indirect probes of higher dimension operators, especially involving the Higgs, because those are the most critical ones for the naturalness question. And every aspect of this machine in the E+E- mode is absolutely amazing. But I'm particularly giddy about the idea of 10 to the 12 Z's. What you could do with 10 to the 12 Z's is just astonishing. And a particularly exciting and powerful probe for the precision electroweak operators, which could give us also a dramatic gain in tuning. There would have to be a lot of work to be done to be able to do that, both experimentally and theoretically. But I think it's a very, very exciting possibility. All right, just to say, there are even more surprising things that could be found. You see, the two scenarios that we're talking about, or a lot of people are talking about, are it could be quite natural, or maybe it's tuned with some anthropic motivations. But something else could happen. I mean, there could be things that happen that there would be sort of no picture for what's going on. At least I would feel I would have to totally go back to the drawing board. In other words, there are fine-tuned theories that we might see that aren't even anthropically motivated. And that would, I think, throw a monkey wrench into the entire structure. Let me just give you one example. Suppose we see at 100 TeV collider the Higgs, and we discover a second Higgs at 1 TeV. Now, we might imagine discovering a second Higgs, I don't know, 700 GeV at the LHC. If we see that, our first Higgs will look tuned, the second Higgs would look perfectly natural. Okay? Well, let's say we go up to 100 TeV, and that's still all we see, just these two Higgses. One at 125 and one at 1 TeV. Now, the first one is tuned at a part in 10,000. The second one is now tuned at a part in 100, and so we have about a part in a million level tuning. Okay? That's even more dramatic than before, and furthermore, has no anthropic explanation whatsoever. The second Higgs has zero purpose in life, and it doesn't, both literally and figuratively. Okay? So if you see something like this, I think not only does it increase the level of tuning, but also it kills almost all the anthropic explanations we could think of, and would really send us back to the drawing board, thinking, you know, these vague words that people say we're thinking about it all wrong. I don't take these things, I'm not very impressed with these vague words, but if something like this happened, I would think that maybe we really are thinking about it all wrong, and it's, not only is it not natural, it's not the landscape, it's really something else. Okay? Now, let's say instead we are just, as we've been before, they're just percentage level accidents, just like in the nuclear physics, moon eclipsing the sun, low power of the CMB. Let's say that's what's going on with the weak scale. Then it's possible we'll see new physics at 13 TeV. It's possible we'll miss it, right? Depends on details at that point. But no matter where the heck it is, the 100 TeV proton-proton collider will just make it. If it's 3 TeV stops, no problem. I'll show you how no problem it is in a second. Well, actually, here it is. I want you to just spend some time staring at this plot. Okay, that's the SUSY reach of a 100 TeV PP collider. Right? Notice the nice large numbers in TeV units. So first of all, at 100 TeV collider, for the first time, we get to use TeV units on our axes. Okay. And just look at this. We're talking about, 20, 25 TeV squarks and gluinos, right? So if we're unlucky and then we're missing the stop, this and that, we'll make everything at a 100 TeV collider. Now, maybe for sake of time, well, maybe I'll say just a little bit about this. A number of people at this meeting have talked about minimally split SUSY. But I just want to say one thing about it. The Higgs mass in minimally split SUSY really favors squarks in the 100 to 1,000 TeV range, which in turn favors gluinos that are not much heavier than 20 TeV. You see, if the gluinos get too much heavier, if they're at 30 or 40 TeV, that pushes the gravitino up, it pushes the scalars up, and it makes the Higgs mass too heavy. So, this minimal picture of a split SUSY really wants gluinos lighter than 20 TeV or so, and that's accessible to a 100 TeV collider. A 100 TeV collider will not necessarily make hundreds of TeV squarks, but it should really catch the gluinos, even if we ignore everything else. I mean, of course, everything could be a lot lighter as well, but it's hard to imagine making things much heavier than that compatible with the Higgs mass. Okay? And of course, a general fact about these split SUSY kinds of spectra is you should expect displacement in the decays of these fermions. The reason is that they can only decay through higher dimension operators. This is also interesting. Let's say we produce gluinos, either at the LHC or at a 100 TeV collider. The fact that they decay inside the detector at all tells you that there has to be, we've seen a higher dimension operator, that there has to be a scale, and the scale is not very far away. The scale is, in the hundreds of TeV range, right? So if you see them decay in the detector at all, whether or not it's displaced or not, if it's displaced, we even get a measure of what the scale is. But seeing them decay in the detector at all tells you that there's a new scale which is not far away and accessible. Okay? So, and in any picture, we're going to want a factory to study these things in as great a detail as possible. So let me not say too much more about that in detail. Now, what if the LHC discovers a relatively natural spectrum? So I was saying, no matter what the LHC discovers, I think we have to go for a 100 TeV collider. So we're going through the possibilities. We did the Higgs and nothing else. Now let's do, we said things like percentage tuning, so we miss some of the particles, split SUSY. What if it's actually natural? What if it's, we turn it on the machine on at 13 TeV, we start making 700 GeV squarks, stops, right? It's relatively natural. Even in this case, we have to go to a 100 TeV PP machine eventually. And the reason is it's not 1995 anymore. In 1995, the mantra was that we'll discover supersymmetry at the LHC, which meant 300 GeV gluinos and everything light, and then we'd study maybe the electroweak particles at a linear collider. That's just not the spectrum anymore. Okay? Everything looks quite a bit heavier than it did before. And even if we discover the new particles at the LHC, the bottom end of the spectrum is implausible to be studied at a low energy E plus E minus machine. And B, even more importantly, the colored spectrum will not be produced in massive numbers at the LHC. If you want an actual factory, you want millions of these particles, it's not going to happen at the LHC, even if we discover them. Okay? And that's why I said it's what we've already seen from the LHC that more motivates going to a 100 TeV. And also, what we've seen from the LHC makes it implausible that even if we do see natural physics, that it's going to be the whole spectrum of the relevant physics at the TeV scale. For example, let's say it's natural SUSY. We see the stops at 600, 700 GeV. Well, the first two generations are going to be heavy. There's no reason they're going to be accessible. In fact, you want to put them at 4, 5, 6 TeV, not to worry about EDMs and other things like that. Okay, well, we'll want to know where the first two generations are. We'll want to know, are they very degenerate? Are they aligned? What's going on with their flavor structure? We want to know a lot about them. No way in heck we're going to study them at the LHC. We'll definitely make them at a 100 TeV collider. Okay. And I said this already. More generally, we're going to want a factory for new colored particles to study how they make the Higgs natural. So we might want to measure the stop-stop Higgs coupling and verify that it's within 10, 20, 30% of its supersymmetric value to see that it's playing the role it needs to play in solving the hierarchy problem. We're not going to do that at the LHC. We could well do that at a 100 TeV collider just because the rates go up by a large power. There's a famous fact about hadron colliders that the rate for producing new physics at a fixed mass scale scales like the 5th to 6th power of energy. So going to 100 TeV increases all the rates for new physics by a factor of 100 to 1,000 to 10,000. Okay. That's the same plot again you can look at to extract that lesson in more detail. All right, so that's the first, that's one set of motivations, is about naturalness. The other two I will go through more quickly. Another thing that a 100 TeV machine does robustly is probe electroweak particles in the TeV range. So if we want to study electroweak physics, electroweak particles that weigh a TeV or 2, We will not do that at the LHC. The LHC will study them at a few hundred GeV, not a few TeV. And that's unfortunate because even WIMPs could very easily be in the low TeV mass range weakly interacting particles. In fact, the very simplest possible picture, the dumbest possible picture for a WIMP, a doublet, okay, a fermion doublet, in order for it to be the thermal relic, as you all know, it needs to weigh 1 TeV, 1 TeV Higgsino, right? No way we're going to see a 1 TeV Higgsino at the LHC directly. We will see it at a 100 TeV collider. And here's a preliminary study that shows what the reach is for WINOs and Higgsinos at a 100 TeV collider versus, and by the way, this is in the most pessimistic possible mode, just monojet, just the monojet mode, not even bothering looking for stubs and displacement and all the rest of it. And as you expect, there's a tremendous gain when you go to 100 TeV. So that's yet another qualitative motivation. You want to study electroweak physics at 1 TeV. The best way of doing it is to go to a 100 TeV PP machine. And finally, I'll make a very brief comment about this. This, I don't think, is the #1 motivation by far, but it's very cool and it's very interesting. And it'll be fun to think about. For the first time, we can start thinking about rich and alive possibilities for collider flavor physics. What I mean by that is that we've known for a long time from FCNCs that we can't generate flavor at the 1 TeV scale. Okay, we can't have a theory of flavor generated at the 1 TeV scale. But you can have a theory of flavor at the 30 or 40 TeV scale. Okay? They're somewhat constrained by thinking about KK bar mixing and other things like that, but it starts becoming a possibility. Many of us talked about theories like this a long, long time ago in lots of different guises. There's no reason it has to be at the 100 TeV scale. It could be related to SUSY breaking, it could be related to all sorts of things, but that's a problem with theories of flavor. They could be generated at the gut scale as well. But it's at least possible to imagine it could be generated at the 50 TeV scale, where it's impossible to even imagine it at the 1 TeV scale. And that means that you can start exploring how you look for signals of that flavor physics at colliders. Just to give you one example, you could imagine that there's some kind of Froggatt-Nielsen structure at the 50 TeV scale. And then you can probe it by now, and that's not dead. That's not dead. You've got to be a little careful about the flavor structure, but it's not dead. And now you can study it. You can study this Froggatt-Nielsen structure by pair producing the Froggatt-Nielsen fields. And because their mass is obviously much larger than the symmetry breaking scale, they have to decay in a way that preserves the flavor symmetries. And so they have to decay through long cascades involving emitting the flavons with extremely interesting signals that I've only started thinking about. I'm just giving it as one example of the sort of new things that become available to think about. Another very simple point. There are so many tops produced at a 100 TeV collider that just the numbers are big enough that you can start probing interesting levels, not contrived made-up theories that give you T to CZ at some rate that's maybe somewhat visible. Reasonable models of flavor gives you FCNCs for tops at reasonable levels that you can see in a 100 TeV machine with this many tops. Okay. And finally, another related point is we, of course, have many ongoing probes from low-energy experiments for CP violation, flavor violation, EDMs, mu-E convert, and so on. If any of these experiments sees a signal, then that's a great thing about these experiments. We get evidence for a new scale. Higher dimension operators in a new scale, and that new scale is in the range, often, not always, but often, certainly for EDMs, maybe for mu-E conversion, depending on the kind of flavor structure that you imagine. Anyway, they're all in the hundreds of TeV range. Some could even be down in the tens of TeV range or lower, which would definitely be accessible to then produce and make at a 100 TeV collider. If the Harvard-Yale group sees a non-zero EDM at the level of 10 to the minus 2080 centimeters, then it's extremely plausible that there are states running around loops generating it that will be accessible to a 100 TeV collider. All right, so those are at least some of the motivations. It's a half-hour concluding talk at the end of a long and exciting meeting, so I didn't. There are many other things that we could talk about and think about. Mostly, I just wanted to whet the appetite of some or many of you to start thinking about this physics. Okay? So just to end, I mean, I personally really believe this. I think we probably all really believe it. That the scientific questions that are at stake in our field now are the deepest ones that we've encountered in over 50 years. Okay? And again, it's not this or that particle. 50 years ago, when the standard model was starting to be developed, the issue was really understanding that quantum field theory did describe the world. That was a very big deal, not to abandon it, finding the sort of correct structure in which to fit any observations we might make. That was all spectacular. But in the end, the standard model so far, except for the unnaturalness of the Higgs, looks like a garden variety quantum field theory. And phenomena like we see elsewhere in the standard model, except for the unnaturalness of the Higgs, are mirrored all over the place in other condensed matter systems. But that's the fascinating thing. What nature has handed us is a deeply unusual quantum field theory in the Higgs sector. Okay? We've never seen anything like it before. And it's structural. It's not about this or that particle. There's something structural, strange, and bizarre about it. Okay? And we need to understand it. And so the questions could not possibly be bigger. And so our ambition should be as big as the questions are. I should also say another totally obvious point. Every single person that I talk to with a pulse, especially people under 35, the second you say the words 100 TeV, their eyes light up, right? And that's because this is their future. It's also my future a little bit, actually. Okay? So, I mean, it's the future of the field. John's too, right? It's the future of all of us. It's the future of the field. But I'm stressing this point about people under 35 because this is your future. And no one is going to make it happen other than you guys and us collectively. But it's really the people who are 35 or under that actually have to do some work to make this happen, right? There's physics work to do. There's lots of other work to do, convincing people, this, that, and the other. But there isn't some cabal of older people in a room smoking cigars saying, now we will support a 100 TeV collider, right? Right? There is no cabal of people. I'm sorry, it's just us, right? And actually, if there was such a cabal of people, they've done a pretty crappy job so far. But anyway, there isn't a cabal anyway. So if you're interested, if you think this is your future, work on it. Okay? Think about it and start thinking about it now. This is a particularly good time to think about it. These 2 years until we start getting new data from the LHC are an outstanding time to start thinking about this. We'll all be so distracted by thinking about whatever we start learning from the LHC afterwards. But if we want to make it happen in your lifetime so it's useful to you, the time to start thinking about it is now. So that's all I want to say, other than just to reiterate that I think this is the obvious future of the field. We can do this. There's nothing stopping us technologically. We can make big tunnels. We have the magnets to do it, or we think we can develop the magnets to do it. Nothing stops us from doing it. We can, so we must. Thank you very much.
Thank you very much, Nima. It's very inspiring. So, questions, disagreements?
My psychology is a bit different because the example that you made of 10 to minus 2 tuning, they suffer from some look elsewhere effect. In the sense, these examples that you can make, the fact that there was a problem that we didn't know the solution, whether it was natural or not, and turns out to be 10 to minus 2 is quite a strong indication, no?
Of something wrong with naturalness. Well, I agree. Those examples have some. We could talk about this more offline. Certainly, the moon eclipsing the sun example has a look elsewhere effect because the moon hasn't been at the same distance even from us over time, right? So it was a little different in the time of the dinosaurs, for example. So it wasn't as good an eclipse then as it is now. So indeed, given that it started off close and it's receding, there's always going to be some time where it looks accidental. So it's really a why now problem. But anyway, I agree. The other examples also, yeah, I agree there's something a little more sinister about the problem in the case of the weak scale. But not enough to me to not think it's a useful analogy still. I think the important thing is we don't know. And had it been like the other cases where it just worked, when it just works, you don't have to argue about this. When it stops working, you have to start if, then, or budding.
Xerxes?
This might be a naive question. You use the 10 to the 4 fine-tuning of the Higgs to argue for the 100 TeV collider.
It's one argument for it, yes.
Yeah, but why are you worrying about the 10 to the 4 when then there is the 10 to the 60 or 10 to the 120 already there?
Absolutely. No, that's really the point. But you know, the problem with the 10 to the 60 or 10 to the 120 with the cosmological constant should have you not even think about low energy supersymmetry at all. But not even think about solving the hierarchy problem at all, right? Why were we all idiots for continuing to think about solving the hierarchy problem, despite the fact that there's a big cosmological constant problem? You know, everyone knew. It's the elephant in the room. You know, in the beginning of almost every talk I gave solving the hierarchy problem 12 different ways, you know, some comment about the cosmological constant, right? Why? It's because we don't, you know, not all problems in nature are solved in the same way. Some problems are solved one way, some problems are related. They may be related, they may not be related. As I said, the cosmological constant problem could have been used as a hammer over the head of people who tried to take the quadratic divergence of the pion seriously. Say, oh, why would you take the quadratic divergence of the pion, charged pion seriously? That's ridiculous. There's this big cosmological constant problem. Well, that turned out to be correct. There is new physics, the rho, it cuts it off. So that's the attitude of everyone who took the hierarchy problem seriously, was we have to ignore the cosmological constant problem when it comes to particle physics. Maybe it's related to cosmology and gravity and mysterious things like that. That may still be true. Okay? But it could also not be true. And it could be that the Higgs is more closely related to the cosmological constant. Now, what I'm saying is that if we discover 550 GeV stops and there's a little squeeze spectrum at LHC 13, okay, then great, it's natural, done. And then too, you'd say, what about the 10 to the 60? Well, I don't know, that's solved with something else. If we don't see anything but the Higgs at the LHC, then we'll be percentage level tuned for electroweak symmetry breaking. Of course, typically in models it's worse than that, but that's a conservative level of tuning that we can conclude. Do we then conclude the Higgs is just like the cosmological constant? It looks like a massive jump to me, and there are so many other examples of these percentage accidents that you could shrug your shoulders. If it clears that bar of things that we've seen before by another factor of 100, that to me seems like a big deal. Now the Higgs is separating itself from the other muck that we've seen and is heading towards what looks like the cosmological constant. Okay? But that's really the question. Is the Higgs tuning like the cosmological constant or not like the cosmological constant? And the LHC will not give us a very clear answer to that question. I think 100 TeV collider. Of course, you could say 10 to the minus 4, what's the big deal? 10 to the minus 6, what's the big deal? This much is subjective, but I want to talk about something invariant. The invariant, is it worse than what we've seen elsewhere? And if it's 100 times worse than what we've seen elsewhere, I think that's very significant.
But it's still a hell of a lot closer to what we have seen.
I completely agree, of course, of course.
More questions?
And this 100 TeV collider is a good idea. We all should pursue it. But what I'm thinking, maybe we need to make more innovative ways to accelerate particles.
Of course.
Not just go to build bigger and bigger machines.
Of course. Well, I mean, I think there are many aspects of a future, if we have a 100 TeV collider, that I think would be amazing. But by the way, one thing is that it doesn't make sense to stop the march of the subject when we can do it. Okay, you know, so it's not like we're not encountering limitations of the size of the Earth or even more, you know, reasonable geographic limitations yet. So we can do it. But I think one wonderful consequence of having something like this in place would be that some fraction of the experimental part of our field will relax and start thinking more focusedly and more ambitiously about novel ideas for going to much, much higher energies. What's going on right now, I mean, they're very serious and very talented people, as I'm sure you know, working on that subject. In my view, there could be a factor of 2 or 3 more people working on that subject. And I think if the long-term 20, 30, 40-year future of our field is set with a 100-kilometer tunnel, 200-kilometer tunnel somewhere in the world, then we can, many of us can sit down. Theorists, experimentalists, lots of people can sit down and think about creative ideas for going to higher energies as well. There's still the century timescale to think about after all.
Yeah, just to mention again, I mean, you mentioned in your previous talk, so you have a new formalism to calculate the scattering amplitude. But the same way, I mean, we have some methodology to do it, but you are struggling for new ways to do it. So the same way we should struggle for new ways to accelerate particles.
I don't think you'll find anyone disagreeing with that statement. I'm saying as a practical fact, if we have this thing sitting there to anchor the development of the subject on the 40-year timescale, it will greatly improve the odds of people now willing to not be stressed all the time and wondering about what they're doing. And just some fraction of people sit down and think more seriously about this question. Not that the people thinking about it now aren't thinking seriously, but to join the effort of these people thinking about it. I can tell you, I will spend time thinking about it.
Will you spend only time thinking about the physics, but also the politics?
Sorry?
Will you spend time only thinking about the physics, but also about the politics, to try to convince...
You know, I think this is an excellent question which cannot be answered in 30 seconds. but obviously, we're not all a bunch of Pollyannas, and you know, we know that there are realities. But something I can tell you is that all of the Machiavellian posturing of the last 20 years, thinking about, oh, we have to say this and do that, and it really hasn't worked, has it?
Okay, with that phrase, Rohini.
While I completely sort of share the excitement about your 100 TeV collider ideas, I think this is partially also a question to John, is that right now, what we do know is that we can have an ILC. We know the technology, we know everything in some sense. And while this is indeed very exciting, and I think that is, I agree that that's the somewhat future aim should be the future aim for us. Don't you also think that it makes sense to think that we should use this, what seems to be a really superb machine for studying the same Higgs?
Again, this is a long discussion we can have about, and it has many aspects to it. I should say that in my view, these questions are, at least in my own view, it's not true for other people. In my view, it's sort of decoupled from what's going on with the ILC. Okay? So I'm interested, you know, of course, I would be, I think getting millions of Higgses at a circular plus/minus machine is awesome, and from all the looks of it, it would give us more precision, not only on the Higgs, go back to the Z, go back to all that is awesome. If there's an ILC, fantastic. And, you know, that there's a wonderful community of people doing this stuff, that's also great. But that does not offer not only Higgs stuff, but also this longer-term future for the field. That's why I was focused. This is why, by the way, this is why in the talk I was focusing on the PP aspect, not because I don't think the plus or minus aspect is important, which it is, and the Higgs factory aspect is important, which it is, but to my mind, the anchor for the whole thing is that it gives this 20, 30, 40-year future of our field.
Okay, well, John?
So just to respond to Rohini, since she mentioned my name. So first of all, I don't think we can take the ILC for granted. The Japanese Science Council has emitted no serious doubts about it. And even the Japanese physicists are saying, well, no, one would need substantial participation by countries outside Asia. And I don't, that's a big political hurdle to cross. And I also believe that TLEP is intrinsically a better Higgs factory than the ILC. But I would agree that if the ILC can go ahead, then without participation from the other regions, then it should. And that would obviously dent the physics case for TLEP, although it would not have any effect whatsoever on the physics case for the 100 TeV machine. So I think that the two visions can coexist.
Comments on that, Nima, just to finish? No? Very good. So this is a perfect way to finish, and we have to let Nima go because he has to catch a flight. Thank you very much.